Alright, hello. So my friend has asked me to go over the Starbase movement for him in some sort of detail, so I'm just going to make a video about it. Um, so let's talk about Starbase movement. So basically, the really what you need to know about the Starbase movement is that my goal is to make it feel really nice. I really want you to be able to position yourself anywhere you want to, and I really want it to feel intuitive. And so that means that I'm going to be drawing from like actual physics rules from reality, and I'm going to be combining them with like not so physics rules, not so realistic physics rules, basically game design. And that creates this like intuitive movement that I'm going to just show you now. So basically, here's an example of what I mean when I like say we're combining physics with video game, because that's like kind of a weird statement. It's obviously you want the game physics to kind of mimic reality in a way, but like whenever you go to program movement systems, there's a lot of things that you don't think about, like air resistance. You don't think about simulating things like air resistance or inertia, and you can simulate those things, but if you do it too realistically, it's not going to lend itself to your game well, because like if I have perfect inertia in Starbase, then like whenever, let's say I go for like I take knockback damage or I go for a weird jump, I'm just going to maintain my speed in such a way that it gets in the way of the gameplay and doesn't let the player position themselves wherever they want to be. So remember our goals for your game. Like you can list out your like list of goals if it's like to make the movement feel good or whatever, then you know you're going to be simulating physics rules in some way. And if your game is to like, if your goals is to like, okay, we're going to give the player a large degree of movement, then you know you're going to be breaking physics rules in some way. And so now let me really describe some of the ways that I do that in Starbase. So the first one is, this is a programmed physics rule. It is an inertia simulation where you jump off, let's say you like jump off of something and the character like maintains horizontal speed. So, right, yeah, that makes sense. Like, that's obvious, but that's not something that is obvious to a programmer, because whenever, like, most programmers, they build movement systems in such a way that, like, you usually stop. I just got a rainbow crit. That was incredibly rare. You usually stop as soon as you, like, let go of the key, and that allows your character to, like, be precisely placed in the world. We don't really want that. Like, we want that option, right? And so I'll talk about how I also broke a physics rule to maintain that option, but I also want it to feel intuitive whenever you're not utilizing that option. So we have two realities. We have one where we have inertia, and we have one where the player cancels the inertia to stop immediately. How do you make this happen in a way that feels good? Because if you just stop immediately, it can feel a little janky, because like things don't stop immediately in real life. So we're going to go ahead, and I might be able to supplement my visual with some of the code. But right. So yeah, we're going to go ahead and look at some of this code here. Code for, let's like go ahead and look. Oh yeah. Before I get to the code, let me define like all of the physics rules that I'm going to go over existing, and then I'm going to go over how I break them in such a way that like it makes the game more easy to control, more precise, but it doesn't feel unintuitive. So the first one is obviously the inertia rule, where you can jump and you maintain your horizontal speed unless you perform a backwards action. This is the part that I left out earlier that I should have talked about, but I'm talking about it now. You jump forward, you maintain your inertia unless you like tap the opposite direction. And if you tap the opposite direction, you in about like 3 or 4 frames, you approach no inertia, and then you start gaining. Sorry, you approach no momentum, and then you start gaining opposite direction momentum. So it's like you can do these. Like, you can, like, it doesn't happen instantly, but you can do these turnarounds in midair that, like, allow you to control yourself really easily. It gives you, like, really good air control. But this is, like, obviously physically inaccurate. The second one is short hops. So the way the jumping system works in this game is, like, we're kind of mimicking, like, Mario, where the longer you hold the button, the further you go up. This is obviously, like, you need to program this specifically to occur only with the player, and it needs to fit into your physics system like really, really well. Finally, I don't even know what I was going to talk about. I just got distracted because my parents walked into my room, but I'm sure we'll discover stuff in the code. So let's go ahead and take a peek here at what we've got. So we're going to go ahead and look at the most of the magic occurs in the acceleration. So I guess we're going to type in acceleration. So here, this honestly expresses most of the h speed, most of the horizontal speed logic. What is happening? Let's just go away, creature. We're going to I'm just gonna here is what I'm gonna do. I'm gonna mute the sound. That's what I'm gonna do. Okay, so the first thing I want to talk about is the inertia. Basically, every component of how the character moves is wrapped up in this one line, and there are multiple components to this. I guess there's a lot of stuff going on here. Let's walk through this one step at a time. So the first thing that we're gonna do, what this block of code does is it literally controls how horizontal speed changes over time. Okay, and so as you can imagine, horizontal speed, like, it should increase if you're moving. It should increase in the direction that you're moving. It should change like friction based on ground type, or it should change friction based on like whether or not you're falling. So it's like we can basically describe every type of interaction, like every like change that can happen to the horizontal speed over time in this one like line of code using the approach function. What the approach function does is it takes this value and moves it toward this value at this rate. In other words, we have a top speed, we have like a target speed that we want to reach, which is described in this equation, and then we have the amount of the number that we're going to use to combine, like we're going to combine this number with this number to get this number, basically every single step. This is something that's meant to happen over multiple frames, and that is inherently going to give us our physical feel where things aren't like super snappy. Things are kind of like, I would say lerpy a little bit. Things lerp a little bit. But yeah, anyways, I think I've rambled a little bit too much. Basically, let's look at inertia now. Let's look at the inertia jumping thing now. So it's like we jump off of a wall. What we want to do is we want to maintain our ability to move in a direction, but we also want to maintain our horizontal speed. So that's basically what these conditions do here. Basically, if we're not moving or we're on the ground, if we are moving or we are on the ground, we're going to use this line of code, which I'm not going to fully describe yet. Or we're going to use this line of code, which is basically, this is basically simulating air resistance. It is, so imagine what I set up here with the approach function. We're taking our current value of h speed. We are approaching the value 0 at a rate of 0.02 per frame. So as long as we're in the air, our horizontal speed is going to slow down at the rate of 0.02. That's what this line of code does. Okay, so this basically means that we maintain our h speed whenever these conditions are not true. That simulates our physical jumping inertia mechanic. Now, the next thing to look at is so let's look at our target h speed. We have basically what we want to do is we have this component, which is the actual value of the target h speed, and this component, which is our direction. So it's either left or right, indicated by 1 or -1. So, well, respectively, it's -1 or 1. So if we want to move left, we're going to multiply this value by -1, and it's going to become a negative value. If we want to move right, we're going to multiply this value by 1, and it's not going to change. So this value is basically our player's base walk speed plus whether or not we are on the ground. So if we are not on the ground, this means that we gain 0.25 top walk speed, which means that while we're in the air, we can actually move faster than when we are on the ground. So let's go ahead and look at this here. I think it would be good to pull up the debugger now. And this is like a really small thing that I didn't even talk about, but we're going to talk about it now. If we look in the bottom left, we have our character speed. You can see it approaching the target value. You can see the direction being expressed in, by the way, it's down here in the bottom left. You can see, yeah, the direction being expressed in the way that the value changes. And whenever we jump, it increases, the top speed increases by 0.25. So that's all that does. And what this does is, like, technically you gain a little bit extra speed while you jump, and it allows you to, it kind of feels, like, this isn't even something that I feel like my players would notice, but it feels nice. It's like in Minecraft, whenever you do, like, your speed jumps and you gain, your top speed increases, it's kind of like that. And it just feels, it feels nice. It feels like I really put a lot more energy into my jump. And there's also this emergent property where you can kind of like b-hop, but it like doesn't really matter because you're not losing speed unless you're on the ground. Oh, I just closed the game. Unfortunately, we'll open it again later. So the next thing to look at is like how fast do we approach the target value? We already know that we're either on the ground or moving, so that's what all these expressions are expressing. So the first thing to notice is that look at these values. You might notice that these might look confusing because you might look at them and be like, oh, this is like somebody calculated these to get the perfect numbers. But no, these are all just kind of like the basic idea is that you move the fastest when you are on the ground, but you're not moving, which means what this is friction. This only happens whenever your character is standing still on the ground and you still have H speed. This is going to only be a part of the equation whenever we are not moving and on the ground. Whenever we are approaching 0, in other words, this is just friction. This is just ground friction, and it only occurs whenever you're not moving. This is air resistance. Wait, is this air resistance? When you're not on the ground, you get 0.1. Right, so this is air resistance, and this is the basic movement speed. In other words, what you need to know about these is that they are only one of these is on at the same. I called this one air resistance. That's false. These only occur at the same time. What this means is that you have more movement speed when you are on the ground, or rather, your acceleration is greater when you're on the ground than it is when you're in the air, by a factor of 0.02, which is conveniently the same number as this one, emergent complexity. And now that we have completed our acceleration analysis, what we can do is move on to the other things. So there's a lot more steps, and here are the other 2 steps. First of all, we have a slowness status effect, which is very simple. As long as you have stacks of slow, we are going to reduce the amount of H speed that you have by 0.9 per frame. In other words, if you have like 3 stacks of slow, then you're going to be completely like you're not going to be moving. This is where some actual magic is happening. So this is something I came up with whenever I was talking about when I was trying to figure out how to simulate the like ability to be precise, the ability to have lots of air control, but also not sacrifice inertia. So let me go ahead and make all of this. So what this few lines of code that I'm about to show you, what these lines of code are. These lines of code, the H speed swap, this is what allows you to like instantly turn around, but like it's not like I'm increasing your movement speed or anything. It's just like you get a little bit of help whenever you want to turn around. So the idea here is that the player will express their desire to turn around by holding an opposite direction to the to where they are moving. And you know what? That's great. But since like the player wants to turn around, we're going to make that happen a little bit faster. And what we do, the way that we do this is we literally just. All right, so I understand that I'm rambling a little bit. What we're going to do instead is we're just going to analyze these conditions. They're really, really simple. So if H move is 1, which means we are moving toward the right, and h speed is less than 0, which means our current h speed, or like our current momentum, is sending us in the left direction. Remember, we want to move right, but we're moving left. Then we're going to take our h speed and divide it by 2, which is going to make it get closer to 0, but it's going to make us closer to 0, but it's not going to be 0, which gives us at least 2 frames of transition period. And then we are going to run the acceleration code, which will add h speed in the direction of in the opposite direction. So this is right. So it's gonna basically what will happen is we're going to approach 0 faster only when we are holding the direction opposite to the direction we are moving. So let's look at this one. You'll see that expressed here. If we are wanting to move left, our input that we're holding is left, but we are currently moving right, or like I guess I should say, and we are currently moving right, then we're going to divide h speed by 2. So this is huge for game feel. This feels amazing. I really love this line of code. It gives you incredible control over your character, but it is not physically accurate at all. Like there's no way that there's no physically logical reason why you should be dividing your momentum by 2. The only reason we do this is because it makes the game feel good. So you need to approach your movement system from the perspective of we need to make it look physically accurate, but we can use game design to make it feel a lot better or give us like otherworldly abilities to position ourselves in space, and that's just, that's everything. So I've rambled I've rambled a lot. I died apparently because I just respawned here. I've rambled a lot, but hopefully this video will express some of the intricacies that went into designing this system, and it's not that hard because you can just, where did I die? It's not that hard because you can just look at your game and figure out what you need and figure out spend an hour just kind of tweaking the values. I think I died down here. Yeah, there I am. But, and yeah, you can spend your hour tweaking the values. You'll approach you'll approach the best movement system possible. It'll feel really nice, and hopefully I've expressed some of my ideas in a way that is understandable, because I understand this very rambly.